Welcome to the Jeremy's IT Lab CCNA Mega Lab. In this lab, we'll cover every configuration topic you need to know for the CCNA exam. Just a warning, this lab is intense. If you've studied all of the exam topics and are getting ready to take on the CCNA exam itself, you've come to the right place. Now, we won't cover every single configuration command you should know, but we will cover all configuration topics on the CCNA exam. IPv4 and IPv6, static routes, VLANs, spanning tree, OSPF, Ether channel, DHCP, DNS, NAT, SSH, security features, wireless, and more. Everything. If you want to dive deeper into any particular topic, such as specific OSPF configurations, you can check out the relevant videos in my CCNA course, or the relevant chapter in my CCNA book. The point of this lab is to tie everything together, instead of focusing on each individual technology or protocol in detail. And the point of this video is to demonstrate the correct solution to this lab, rather than to explain the details of each concept again. You may notice that this lab file isn't a typical .pkt packet tracer file. It's a .pka packet tracer activity file. PKA files include automated grading, so after you complete the lab, you can click Check Results here to see if you configured everything correctly. Now, by default, the instructions here are a separate window like this, but I'll click Dock here to dock them into the same window as the lab topology, so we can easily see the instructions as we go through the lab. The network topology for this lab is a 3-tier LAN consisting of two offices, Office A on the left and Office B on the right. The two offices are connected via a core layer, and R1 provides internet access with two redundant connections. If you click on the internet here, you can see it simply consists of two routers that I have labeled ISP-A and ISP-B. You don't have to worry about these routers for this lab. You only need to configure the network from the perspective of the customer of these ISPs, the enterprise connected to the internet. So click on this back arrow here to return to the rest of the network. So before diving in, let's read the lab introduction here. It says this comprehensive lab covers all configuration topics on the CCNA exam. Proceed through the steps in order, and click Check Results when you are done to check your configurations. So as you can see here, this is page 1 of 10. You can click Next to go through the different pages to see the different steps. But there is an important note here that says you must save the device configurations, for example with the copy running config startup config command, or you will receive no points. The grading system for most of this lab checks the startup config of each device to make sure it matches the one I prepared beforehand. So make sure to save each device's configuration, or you won't get points. And finally, at the bottom, it says this lab is quite extensive, so you should set aside at least a couple of hours to finish all of it. Here at the start of this video, I have no idea how long the video itself will be, but I do know it's going to be the longest video I've ever made. So enough talking. I'll click on Next to begin part 1 of this lab, which is Initial Setup. So we are going to configure 4 main things in this section. In step 1, we'll configure the host name of each router and switch. In step 2, we'll configure an enable secret to protect access to privileged exec mode. In step 3, we'll configure a user account. And then in step 4, we'll configure the console line of each device. So let's start with step 1, configuring host names. I'll open the CLI of R1. Now, recording this video on a single screen is a bit of a challenge. Ideally, I'd like to show the instructions, the topology, and the CLI all at once, but there's just not enough real estate on the screen. So I've prioritized making the CLI larger, so you can see all of the configurations easily. I'll show the instructions in between each step, but while we're doing the configurations, you won't be able to see them. So first I'll use enable to enter privileged exec mode here on R1. Then conft to enter global config mode, and then hostname R1 to configure the router's hostname. The hostnames must match what's shown in the diagram here. Okay, I configured R1's hostname, but if I look at the lab instructions, notice that the completion rate is still 0%. That's because the evaluation is checking the device's startup config, but the command I just entered only changed the running config. To copy that configuration to the startup config, I'll use do write, but you could also use write memory or copy running config startup config. All three commands have the same effect. Then go back to check the completion score again, and now we're at 1%. Because you have to configure many hundreds of commands in this lab, don't expect the completion score to increase after every single new command you configure. However, as you go through the lab, I recommend saving the device configurations and checking that the score is increasing as you proceed. Now I'll configure the host names of the core, distribution, and access switches. For the sake of completeness, I will show all of these configurations in this video, but feel free to skip ahead if you don't want to watch these repetitive commands. So I'll open up cswitch1. Enable conft hostname cswitch1, and I'll save the configuration with do write. Next, cswitch2. Enable conft hostname cswitch2, and save the config with do write. Next up we have the distribution switches, dswitch A1 and A2, and dswitch B1 and B2. I'll start with dswitch A1. Enable conft hostname dswitch A1, do write. Then dswitch A2. Enable conft hostname dswitch A2, do write. Next, in Office B, dswitch B1. Enable conft hostname dswitch B1, do write. Finally, dswitch B2. Enable conft hostname dswitch B2, do write. Finally, the same deal on the access switches, starting with aswitch A1. Enable conft hostname aswitch A1, and save the config with do write. Then aswitch A2. Enable conft hostname aswitch A2, do write. Then A3. Enable conft hostname aswitch A3, do write. Then move on to Office B, starting with aswitch B1. Enable conft hostname aswitch B1, do write. Then B2. Enable conft hostname aswitch B2, do write. Finally, B3. Enable conft hostname aswitch B3, do write. Okay, let's take a look at the instructions again. Take a look at the completion score. It's increased a lot already. Don't get too excited, we're just getting started. When the lab first starts, the devices all have no startup config, so there's nothing to evaluate. But when you first save the configs, various default configurations like interface names are saved to the startup config. That's why the score jumps up after just configuring the host names and saving the configs. From now on, I won't save the configs after every single step. I'll just save them after each section of the lab to show how the score increases as we progress. Now let's look at steps 2, 3, and 4 together. Step 2 says to configure the enable secret Jeremy's IT lab on each router and switch. It also says to use type 9 hashing if available, or type 5 if type 9 isn't available. Let's hop on R1 again to demonstrate. From global config mode, type enable, and then a question mark to view the iOS context-sensitive help. So the options are password and secret. Now let's go to a different device, cswitch1, and see the options. Again, type enable and a question mark to see the options. Notice there is a third option, algorithm type. This lets you specify the hashing algorithm that is used to hide the enable secret in the config. I cover this command in my book Acing the CCNA Exam, but I haven't covered it in my video course, so you might not be aware of it. At some point, I'll update the course and include it. Anyway, in Packet Tracer, these core and distribution switches, which are Catalyst 3650 switches, support this command, and you can use type 9 hashing on them. But the other devices, including R1 and all of the access switches, don't support the command. They only support type 5 hashing, which is MD5. So I'll return to R1. Configure the enable secret with enable secret Jeremy's IT lab. And then check with do show run, use the pipe to filter the output, then include secret. As you can see, the secret is hashed using type 5, which is MD5. And then on cswitch 1, I'll do enable algorithm type, and then use a question mark again. It has the scrypt option. This is type 9 hashing. It uses the scrypt hashing algorithm. So let's finish the command. Enable algorithm type scrypt, secret Jeremy's IT lab. And let's check. Do show run, pipe include secret. So as this number 9 indicates before the hash, the secret was hashed using the type 9 algorithm, scrypt. So we'll configure type 9 hashing on the core and distribution switches, and type 5 on R1 and the access switches. But before we do that, let's check out steps 3 and 4. Step 3 says to configure the user account Cisco with the secret CCNA on each device. And it says the same thing about hashing. Type 9 if available, and type 5 if not. Just like the enable secret, in Packet Tracer, these multi-layer switches in the core and distribution layer support type 9, but R1 and the access switches only support type 5. Once again, let me demonstrate that in the CLI, on R1 first. First type username, then the username Cisco, and then the question mark. There is no option for algorithm type, so I'll just type secret, and then the password CCNA. Let's check again with do show run, pipe include secret. Like the enable secret, this user account secret was hashed with MD5, which is type 5 in iOS. Now let's compare that with cswitch 1. First type username Cisco, and then use the question mark. This one has the algorithm type option, so I'll type that, followed by scrypt, then secret, and then the secret CCNA. And let's check. Do show run, pipe include secret. So both the enable secret and this account secret were hashed with the scrypt algorithm, which is type 9 in iOS. So on these multi-layer switches in the core and distribution layers, we'll use type 9, and on R1 and the access switches, we'll use type 5. But before doing that, let's finally take a look at step 4. Step 4 says to configure the console line to require login with a local user account, set a 30-minute inactivity timeout, and enable synchronous logging. So that requires 3 configuration commands, and these will be the same on all of the devices. I'll show them on R1 first. First, use line console 0 to configure the console line. There's only one. The first instruction was to require login with a local user account. The command to enable that is login local. Now, when someone connects to the device console port, they will have to log in using a user account on the device, such as the Cisco account we just created. The next instruction was to set a 30-minute inactivity timeout, meaning that the user will be logged out after 30 minutes of inactivity. I'll use the question mark, and here you can see the command, exec timeout. Type the command, and then the time in minutes, so 30. You can also specify seconds after, for example 30 minutes and 30 seconds, but we don't need to in this case. Finally, we should enable synchronous logging. The command for that is logging synchronous. With that enabled, if a syslog message appears while I'm in the middle of writing a command, the command will be reprinted on a new line, making it easier to see the command I'm typing. It won't be cut off by the log message. Okay, I've finished steps 2, 3, and 4 on R1. So I'll use do write to save, and exit to return to global config mode. Now for the rest of the devices, I'm simply going to copy and paste the commands. When you're doing large labs like this that require configuring the same commands on many devices, this is a great technique to speed things up and also avoid typos and misconfigurations. So I've prepared the commands in a text file, but I won't include it in the lab files. When you do the lab, you can either type the commands directly into the CLI, Or you can do what I did, prepare the commands in a text file like this, and then copy and paste them into the CLI. So at the top here are the commands for R1 and the access switches, the enable secret, the user account, and the console line configurations. I'm going to copy them with Ctrl-C, and then paste them into the access switches, since I already configured R1. Let's do it on ASwitch A1 first. To paste the commands in Packettracer, right-click in the terminal, and then click on Paste. There we go. All of the commands were pasted in. Finally, I'll just save the config with do right, and return to global config mode with exit. Next, ASwitch A2. Right-click, paste, do right, and exit. Then A3. Right-click, paste, do right, and exit. Now move on to Office B, ASwitch B1 first. Right-click, paste, do right, and exit. Then B2. Right-click, paste, do right, and exit. And finally, ASwitch B3. Right-click, paste, do right, and exit. So R1 and the access switches are done. Now let's take a look at that notepad again and scroll down. These switches in Packettracer support type 9 hashing for the enable secret and user accounts. So we'll use those commands that I showed before on CSwitch 1, and also configure the console line. So highlight and copy all of these commands, and let's go on CSwitch 1. We already configured the enable secret and user account here, but not the console line. I'll just paste all of the commands in anyway. Right-click, paste, do right, and exit to return to global config mode. Next up, CSwitch 2. Right-click, paste, do right, and exit. Then the distribution switches. DSwitch A1 first. Right-click, paste, do right, exit. Then DSwitch A2. Right-click, paste, do right, and exit. DSwitch B1 next. Right-click, paste, do right, exit. And finally, DSwitch B2. Right-click, paste, do right, exit. Okay, we finished part 1. Notice that the completion score has increased a few points. Still a long way to go, so let's click Next to go to part 2. Part 2 covers VLAN and Layer 2 Ether channel configurations. So we'll be focusing on the distribution and access switches in this part. First, let's quickly look at the instructions. Step 1 says to configure a Layer 2 Ether channel between DSwitch A1 and A2 in Office A, using a Cisco proprietary protocol. And Step 2 says the same for DSwitch B1 and B2, but says to use an open standard protocol. So a Cisco proprietary protocol means we'll configure PAGP, Port Aggregation Protocol, between DSwitch A1 and A2, and an open standard protocol means we'll configure LACP, Link Aggregation Control Protocol, between DSwitch B1 and B2. Okay, Step 3 then says to configure all links between access and distribution switches, including the Ether channels, as trunks. So all of these links here should be trunks. In Step 4, we'll configure VTP on these switches, so they can sync their VLAN databases automatically. Then in Steps 5 and 6, we'll create the appropriate VLANs in Office A and Office B. And in Steps 7 and 8, we'll configure each access switch's interfaces connecting to end hosts. And finally, in Step 9, disable unused ports. So that's Part 2, focused on various Layer 2 concepts. Let's start by configuring those Ether channels. First, I'll do Step 1, focusing on DSwitch A1 and A2. We already established that we'll configure this one using the Cisco proprietary PAGP, but notice also that it says both switches should actively try to form an Ether channel. PAGP has two modes, desirable and auto. This means we should configure both sides to use the desirable mode, which actively tries to form an Ether channel. Auto mode will form an Ether channel with a neighbor in desirable mode, but doesn't try to form an Ether channel itself. So I'll go on dswitch A1 first. Now there are no interface labels on these devices. To see them, you can turn on interface labels in Packet Tracer settings. Or you can look at the spreadsheet that I included in the lab files. It lists all of the connections between devices. You can get the lab files at this URL, jitl.jp/mega-lab. But the best method is to practice your CLI skills and use do show CDP neighbors. In the output of this command, you can see that dswitch A1 is connected to dswitch A2 via its G104 and G105 interfaces. The local interface column lists the interface on this switch, dswitch A1. And on the final column on the right, you can see that the same interfaces are used on dswitch A2, G104 and G105. So I'll use interface range G104 to 5 to configure both interfaces at the same time. Then just use channel group 1 mode desirable to configure these interfaces as part of port channel 1. Now, how do you know which group number to use? Look carefully at the lab instructions. It says configure a layer 2 ether channel named port channel 1. This number, the port channel number, is the group number. Make sure to pay close attention to these instructions. If you use a different group number, it won't be marked correctly when you click on Check Results at the end of the lab. Okay, now let's do the same on dswitch A2. Interface range G104 to 5. Channel group 1 mode desirable. And just to make sure, I'll check its status with do show ether channel summary. So here's port channel 1. It has the flags S and U, meaning layer 2 and in use, so that's good. And the member ports both have the flag P, meaning in port channel. So everything looks good. Next, let's configure the ether channel between dswitch B1 and B2. LACP has two modes: active, which is like PAGP's desirable mode, and passive, which is like PAGP's auto mode. Like step 1, step 2 says that both switches should actively try to form an ether channel, so we'll use active mode. So let's go on dswitch B1. Like the Office A switches, these two are connected via G104 and 5, so interface range G104 to 5. Then channel group 1, mode active. That's it. I'll do the same on dswitch B2. Interface range G104 to 5. Channel group 1, mode active. And just to make sure it's okay, I'll check with do show ether channel summary. So we see the SU flags on the port channel interface, and the P flag on the physical interfaces, so all's good. Now let's move on to step 3, which says to configure all links between access and distribution switches, including the ether channels, as trunks. There are a few requirements. First, it says to explicitly disable DTP on all ports. We'll use switch port no negotiate for that. Then, it says to set each trunk's native VLAN to VLAN 1000, which is unused. That's a good security measure. The native VLAN can make the LAN vulnerable to VLAN hopping attacks. Then, we should allow VLANs 10, 20, 40, and 99 on all trunks in Office A, and allow VLANs 10, 20, 30, and 99 on all trunks in Office B. When we configure the VLANs later, we'll see the purpose of each of those VLANs. For now, just make sure to assign the correct VLAN numbers. Okay, first let's focus on Office A. On each distribution switch, we need to configure these 3 links to the access switches as trunks, as well as the port channel between the distribution switches. So I'll hop on dswitch A1. First, let's confirm the correct interfaces with do show CDP neighbors. So A switch A1, A2, and A3 are connected to this switch's G101, 102, and 103 interfaces. So let's configure those interfaces as trunks. Interface range G101 to 3. First use switch port mode trunk to make the interfaces trunks. Now, the instruction said to explicitly disable DTP on the ports. Even when manually configured in trunk or access mode, DTP is still technically enabled, so let's disable DTP with switch port no negotiate. Next, I'll set the native VLAN with switch port trunk native VLAN 1000. Finally, set the allowed VLANs. This is Office A, so I'll use switch port trunk allowed VLAN 10, 20, 40, 99. Next, I'll use the same commands on port channel 1. Interface port channel 1, switch port mode trunk, switch port no negotiate, switch port trunk native VLAN 1000, and switch port trunk allowed VLAN 10, 20, 40, 99, and then exit. Okay, we're done configuring dswitch A1. These commands will be similar on most switches, so I'll just copy and paste the commands on the others. Let me open up the notepad I prepared and scroll down to part 2, step 3. First, I'll copy these commands to configure on dswitch A2, identical to the commands on dswitch A1. And now, let's go to dswitch A2, right-click, and paste them. Then, I'll use exit to return to global config mode. You don't have to exit after each step, by the way. It's just a habit of mine. Okay, now let's go back to the notepad and check the commands for the access switches in Office A. They are connected to the distribution switches via their G01 and G02 interfaces. So the first command is interface range G01 to 2. Then the configuration commands are the same as the other trunks. So let me copy these commands, and first I'll go on ASwitch A1. Right-click, paste, exit, then ASwitch A2, right-click, paste, exit, finally ASwitch A3, right-click, paste, exit. Okay, Office A is done. Now let's go back to the notepad for the Office B switches. The configurations for these switches are nearly identical to Office A. The only difference is that Office B uses VLAN 30 instead of VLAN 40. Just like in Office A, we'll make the interfaces trunks, disable DTP with switch port no negotiate, configure the native VLAN, and allow only the required VLANs. So let me copy the configurations for the distribution switches. Now let's paste them into dswitch B1 first. Right-click, paste, exit. Then dswitch B2. Right-click, paste, and exit. Now let's go back to the notepad and copy the configurations for the access switches. Then paste them into the switches, starting with ASwitch B1. Right-click, paste, exit, then B2, right-click, paste, and exit, and then B3. Right-click, paste, and exit. That's all for step 3. Next, let's look at step 4. It says to configure one of each office's distribution switches as a VTP v2 server, using domain name Jeremy's IT Lab. Then, we'll verify that other switches join the VTP domain, and configure all access switches as VTP clients. These configurations won't take too long, so I'll do them manually. In Office A, I'll configure VTP on dswitch A1, and it should propagate the configurations to the other switches. First, I'll use do show VTP status to confirm the default state. So the default VTP domain name is null, no domain name. The default version is 1, and the default operating mode is server. So we just need to configure a domain name and enable VTP version 2. VTP domain, Jeremy's IT Lab. Make sure you get the capitalization correct. These are case sensitive. Then VTP version 2. Making these configurations should cause dswitch A1 to send VTP advertisements, and the other switches should join the domain. Let's check on one other switch to verify, like ASwitch A3. Do show VTP status. Okay, ASwitch A3 is running VTP v2 and has joined the Jeremy's IT Lab domain. Now, since step 4 also said to make the access switches VTP clients, I'll do that now on this switch. VTP mode client. And let's do it on the others. I'll go on A2 next. VTP mode client. And then A1. VTP mode client. Okay, so Office A is done, but Office A's VTP advertisements won't reach Office B. VTP advertisements are only sent out of trunk ports, and we haven't configured these links between the distribution and core switches as trunks. They're currently all in access mode. Later, we'll make them layer 3 links. So the point is that we need to activate VTP in Office B too. I'll go on dswitch B1. Let's configure the domain. VTP domain, Jeremy's IT lab. And then VTP v2. VTP version 2. Instead of checking on this switch, I'll just check on a switch B3. It should have joined the domain already. Do show VTP status. Okay, VTP v2 and domain name Jeremy's IT lab. Now let's configure these access switches as VTP clients. VTP mode client. Then a switch B2. VTP mode client. And finally, a switch B1. VTP mode client. Okay, step 4 is now complete. In steps 5 and 6, we'll create and name the VLANs in these two LANs. In Office A, VLAN 10 is for PCs, VLAN 20 for phones, VLAN 40 for Wi-Fi, and VLAN 99 for management. Office B is similar, but instead of VLAN 40 for Wi-Fi, it has VLAN 30 for servers. As a side note, why do you think that only Office A has a Wi-Fi VLAN, even though Office B also has an access point? Think about that. We'll address it later. So thanks to VTP, we only have to do these configurations on a single switch in each VLAN. VTP should propagate the changes to the other switches. So I'll go on dswitch A1 again. First, I'll make VLAN 10 and name it with the command name PCs. Then VLAN 20. Name it with name phones. Then the Wi-Fi VLAN, VLAN 40. Name Wi-Fi. And finally, VLAN 99, name management. Exit. Let's double check them with do show VLAN brief. Okay, 10 PCs, 20 phones, 40 Wi-Fi, and 99 management. Now let's check on a switch A3 again to make sure that VTP propagated the changes. Let's use do show VLAN brief here. Perfect. It has the same 4 VLANs with the correct names. Now let's do the same in Office B. I'll configure the VLANs on dswitch B1. First, VLAN 10, name PCs. Then VLAN 20, name phones. Office B has server 1, so I'll create VLAN 30 and name it with name servers. Finally, VLAN 99, name management. Exit. This time, I won't even check the VLANs on this switch. Let's just go to a switch B3 and verify that it has synced its VLAN database. Do show VLAN brief. Okay, it has VLAN 10 for PCs, VLAN 20 for phones, VLAN 30 for servers, and VLAN 99 for management. That's all for steps 5 and 6. In step 7, we'll configure each access switch's access port. Of course, in a real network, you can expect many more end hosts. But in a practice lab like this, there's not much point in connecting dozens of PCs to these switches. It just clutters up the screen. So, a switch A1 and B1 are both connected to lightweight APs, LWAPs. As step 7a says, LWAPs will not use FlexConnect. That means that all traffic will be tunneled to WLC1 in the management VLAN, VLAN 99 in this case. So these connections to LWAPs can be access ports. They only need to support the management VLAN. By the way, this is also the reason why Office B doesn't have a Wi-Fi VLAN. Traffic from wireless clients in Office B is tunneled to WLC1 in Office A, and only then is assigned to VLAN 40, the Wi-Fi VLAN. So let's configure a switch A1 and B1 first. Before we go to a switch A1, Notice that step 7D says to manually configure access mode and explicitly disable DTP. So these ports are in dynamic auto mode by default and will operate as access ports. But for this lab, we need to manually configure access mode and disable DTP. Okay, let's go on A-switch A1. These end hosts are connected to each switch's Fast Ethernet 01 interface. So I'll configure interface F01. First, manually configure access mode with switchport mode access. DTP is disabled as a side effect of this command. It will not send or accept DTP messages. However, the instructions say to explicitly disable DTP, and the command to do that is switchport no negotiate. The command is redundant in this case, since configuring access mode stops the port from sending or accepting DTP messages, but make sure to read each step carefully and not miss any configurations, especially on the CCNA exam. Finally, let's assign this port to the management VLAN. Switch port access VLAN 99, and then exit. Okay, now let's do the same on A-switch B1. Interface F01, switch port mode access, switch port no negotiate to explicitly disable DTP, and then switch port access VLAN 99, exit. Okay, these two switches are done. Next, let's configure A-switch A2, A3, and B2, which are connected to IP phones in VLAN 20 and PCs in VLAN 10. Since these three switches will all have the same configurations, let's copy and paste them. In my notepad, I'll scroll to Part 2, Step 7, and here are the commands. First, configure access mode and explicitly disable DTP. Then configure access VLAN 10 for the PCs and voice VLAN 20 for the phones. So I'll copy these commands and I'll paste them into A-switch A2 first. Right-click, paste, and exit to return to global config mode. Then A-switch A3. Right-click, paste, and exit. Finally, A-switch B2. Right-click, paste, and exit. Finally, we also need to configure A-switch B3's connection to server 1 in VLAN 30, the server's VLAN. So on A-switch B3, configure interface F01, switch port mode access, switch port no negotiate, switch port access VLAN 30. Exit. Okay, step 7 is done. Next, let's do step 8, which says to configure A-switch A1's connection to WLC1. There are 3 points. It must support the Wi-Fi and management VLANs, the management VLAN should be untagged, and we must disable DTP. So, I'll configure it as a trunk port that allows both VLANs, assign the management VLAN as the native VLAN, and use switch port no negotiate to disable DTP. Okay, let's go on A-switch A1. WLC1 is connected to F02, so interface F02. Make it a trunk with switch port mode trunk. Allow only the Wi-Fi and management VLANs. Switch port trunk allowed VLAN 4099. Configure the management VLAN as the native VLAN. Switch port trunk native VLAN 99. And then disable DTP. Switch port no negotiate. Exit. Okay, that's step 8. Finally, in step 9, we'll administratively disable all unused ports on access and distribution switches. So, let's go on D-switch A1 to confirm which ports we need to disable. To check, use do show interfaces status. So, all of these interfaces with the status not connect aren't connected to another switch and should be disabled. So, that's G106 to 1024 and G113 and 114. So let's disable them all at once. Interface range, G106 to 24, then a comma, and G113 to 4. Okay, now disable them with shutdown. And then I'll use exit. Let's check with do show interfaces status again. Okay, all of the not connect interfaces are now disabled. And because this is the last step of this part, I'll also use do write to save the config. Now the other distribution switches use the same interfaces. So to disable their unused interfaces, I'll just copy and paste the commands from my notepad. Here it is. Interface range G106 to 24, G113 to 4, and then shutdown. I'll copy these commands and then paste them into dswitch A2 first. Right-click, paste, exit, do write. Then B1. Right-click, paste, exit, do write, and finally B2. Right-click, paste, exit, do write. Okay, next up, we'll disable unused interfaces on the access switches. First, I'll go on A-switch A1. Let's see which interfaces are in use with do show interfaces status. So, F01 is connected to an LWAP, and F02 to WLC1. Then G01 and 02 are connected to the distribution switches. So we should disable these remaining fast Ethernet interfaces, F03 to 24. Interface range, F03 to 24, shutdown, exit, and then do write to save. Now the other access switches are a bit different. They only have end hosts connected to their F01 interfaces. They don't have a WLC connected like A-switch 1 does. So instead of disabling F03 to 24, we'll disable F02 to 24. I'll copy and paste the configurations from my notepad. Here are the commands. Interface range F02 to 24, shutdown. Copy those commands, and then I'll paste them into A-switch A2 first. Right-click, paste, exit, do write. Then A3. Right-click, paste, exit, do write. Move on to A-switch B1 next. Right-click, paste, exit, do write. Then B2, right-click, paste, exit, do write, and finally A-switch B3. Right-click, paste, exit, do write. Okay, that's step 9, and now part 2 of the lab is complete. Look at the completion score. We aren't actually halfway through the lab, because we got a big boost after configuring the first step, but we've made some good progress. Now let's click Next to move on to part 3. Part 3 covers IP addresses, Layer 3 Ether channel, and HSRP, Hot Standby Router Protocol. This part has a lot of steps, most of it involving configuring IP addresses, so I'll do lots of copying and pasting here. All of the IP addresses are given in the instructions, but you can also take a look at the spreadsheet in the lab files. The second tab in the spreadsheet has a chart showing all of the IP addresses that you can refer to. But let's get started with step 1, which involves configuring R1's interfaces. G000 and G010 are connected to the internet, and they will use DHCP to learn their IP addresses. Then, we'll manually configure 10.0.0.33/30 on G00, .37/30 on G01, and create and configure an IP address on loopback 0, 10.0.0.76/32. So let's go on the CLI of R1. First, I'll configure G000 and G010 with interface range G000, a comma, and then G010. Use IP address DHCP to make them learn their IP addresses via DHCP, and don't forget no shutdown to enable them. Router interfaces are disabled by default. Next, let's configure G00. This is the interface connected to C-switch 1. Interface G00, IP address 10.0.0.33, 255.255.255.252, no shutdown. Then G01, the interface connected to C-switch 2. Interface G01, IP address 10.0.0.37, 255.255.255.252, no shutdown. And finally, create loopback 0 with interface loopback 0 and configure IP address 10.0.0.76 and a /32 netmask. So let's check R1's interfaces with do show IP interface brief. Okay, G000 and 010 learned IP addresses via DHCP, and G00, G01, and loopback 0 have the IP addresses we configured. This is the only step involving R1 in this section of the lab, so I'll use do write to save its configuration. Before moving on, let's take a look at that spreadsheet I mentioned a couple of times. It might be useful when you do this lab. The first tab lists each device's physical connections. For example, here at the top left, we can see that R1G00 is connected to C-switch1 G101, and G01 is connected to C-switch2 G101. Feel free to refer to this chart, or use Show CDP Neighbors in the lab to figure out how the devices are connected. Then in the IPv4 tab, you can see each device's IP addresses. For example, on the R1 to ISP-A link, you can see the subnet here, 203.0.113.0/30. Here is ISP-A's IP address, 203.0.113.1, and here is R1G000's address, .2, which it learned via DHCP. All of the other subnets are listed here too. R1 to ISP-B, the management subnet for Office A, the management subnet for Office B, etc. Once again, feel free to refer to this chart as needed as you configure this lab. Okay, let's return back to the lab itself. Step 1 is complete, so let's move on to Step 2, which says to enable IPv4 routing on all core and distribution switches. That just requires a single command on each switch, IP routing. So let's quickly do that on each of them, starting with C-switch1, IP routing. Then C-switch2, IP routing. D-switch-A1, D-switch-A2, D-switch-B1, and D-switch-B2. Okay, that's all for Step 2. Next, in Step 3, we'll create a Layer 3 Ether channel between C-switch1 and C-switch2 using a Cisco proprietary protocol, so PAGP, and both should actively try to form an Ether channel, so we'll use desirable mode. The subnet is 10.0.0.40/30, and C-switch1 should use .41 and C-switch2 .42. Okay, let's configure that on C-switch1 first. First, let's see which interfaces are connected to C-switch2. Do show CDP neighbors. Okay, we can see two entries for C-switch2, connected to C-switch1's G102 and G103 interfaces. And they are connected to the same interfaces on C-switch2, G102 and 3. So let's configure them with interface range G102 to 3. First, I'll make them routed ports with no switch port. Then, make the Ether channel with channel group 1, mode desirable. A Layer 3 Ether channel's IP address must be configured on the port channel interface. So, interface port channel 1. IP address 10.0.0.41 and a /30 netmask. Now let's do the same on C-switch2. Interface range G102 to 3, no switch port, channel group 1, mode desirable. Then configure the port channel. Interface port channel 1, IP address 10.0.0.42, and a /30 netmask. Okay, let's check the Ether channel with do show Ether channel summary. So on port channel 1, RU means layer 3 and in use, which is good. And the member ports both have the P flag, which is also what we want. Let's quickly test by pinging C-switch1. Do ping 10.0.0.41. Because the ARP process in Packet Tracer is slow, you might see the first ping or two timeout, but then the others work. And if you ping a second time, they all work. Okay, that's all for Step 3. Next, let's look at Steps 4 and 5 together, which involve configuring the appropriate interfaces on C-switch1 and C-switch2. We just configured the Ether channel that connects them, and now we have to configure their other interfaces, which should all be routed ports. Their G101 interfaces connect to R1. C-switch1 G101 is 10.0.0.34/30, and C-switch2 is .38. Then, their G111, 2, 3, and 4 interfaces each connect to the distribution switches. Then, configure a loopback interface on each of them. Finally, notice that it also says to disable all unused interfaces. Remember that as a security best practice. So you can see all of the IP addresses here. I don't think you need to see me configuring these IP addresses one by one, so let's look at the commands in the notepad, and then I'll just copy and paste them. So here we are, Part 3, Step 4, C-Switch 1. On each of its physical interfaces, I'll first use no switch port to make it a routed port, and then just configure the IP address. Then I'll configure loopback 0 and disable the unused interfaces, which are G104 to 24. So I'll highlight and copy all of these commands. Then I'll go into the CLI of C-Switch 1, right-click, and paste them, and then exit. This is actually the last step that involves C-Switch 1 in this part of the lab, so I'll use do write to save the configuration here. Now let's do the same for C-Switch 2. I'll go back to the notepad and scroll down to Part 3, Step 5. So the commands for C-Switch 2 are identical, aside from the different IP addresses. So let's highlight and copy these commands, go to the CLI of C-Switch 2, right-click, and paste them in. Then I'll exit and use do write to save the config. Okay, steps 4 and 5 are complete. Now let's do steps 6, 7, 8, and 9 together, which involve configuring IP addresses on the distribution switches connections to the core switches, as well as a loopback interface on each distribution switch. Like steps 4 and 5, these steps just involve configuring IP addresses on interfaces, so I'll copy and paste them from my notepad. First, here's Part 3, Step 6, configuring dswitch A1. On G111 and G112, the connections to C-Switch 1 and C-Switch 2, we'll configure 10.0.0.46/30 and .62/30, and then we'll create loopback 0 and configure .79/32. So I'll copy these commands, paste them into dswitch A1 CLI, and then exit. Then I'll go back to the notepad for Step 7, configuring dswitch A2. The commands are the same, just with different IP addresses. So I'll highlight and copy these commands, go into the CLI of dswitch A2, right-click, paste, and then exit. Okay, back to the notepad for dswitch B1, which is Step 8, configuring .54/30, .70/30, and .81/32 on the loopback. So highlight and copy these commands, go into the CLI of dswitch B1, right-click, paste, and then exit. And finally, go back to the notepad for Step 9, configuring dswitch B2. I'll highlight and copy these commands, go to the CLI of dswitch B2, right-click, paste, and then exit. Okay, steps 6, 7, 8, and 9 are done. We've configured IP addresses on the distribution switch's physical and loopback interfaces. Step 10 is a bit different. Instead of configuring IP addresses in the iOS CLI, we'll configure Server 1's IP settings in the Packet Tracer GUI. Default gateway 10.5.0.1, IPv4 address 10.5.0.4 with a /24 subnet mask. So, after clicking on Server 1, go to the Config tab. Here, we can configure Server 1's IPv4 default gateway, 10.5.0.1. Then, on the left, click on Fast Ethernet 0, and then IPv4 address 10.5.0.4. It uses a /8 subnet mask by default, because it's a Class A address, but change that to /24. Okay, we've configured Server 1's IP settings, so that's all for Step 10. Step 11 says to configure the following management IP addresses on the access switches, using the VLAN 99 interface, and configure the appropriate subnet's first usable address as the default gateway. So these access switches are Layer 2 switches, but we want to be able to connect to them remotely for configuration via SSH, so we need to configure an IP address and default gateway on each of them. A-switch A1, A2, and A3 have IP addresses in the 10.0.0.0/28 subnet, so we'll configure the first usable address of that subnet, .1, as their default gateway. A-switch B1, B2, and B3 have IP addresses in the 10.0.0.16/28 subnet, so we'll configure .17 as their default gateway. Let's start in Office A with A-switch A1. To configure a Layer 2 switch's default gateway, use IP default gateway and then the IP address, 10.0.0.1. Now let's configure the VLAN 99 SVI. Interface VLAN 99, IP address 10.0.0.4, and the prefix length is /28, so 255.255.255.240. Exit. This is the last step involving these access switches in this part of the lab, so I'll use do write to save the config. And now let's move on to A-switch A2. Same default gateway. IP default gateway 10.0.0.1. Interface VLAN 99, IP address 10.0.0.5, and a /28 netmask. Exit. And save the config with do write. And then the same on A-switch A3. IP default gateway 10.0.0.1, interface VLAN 99, IP address 10.0.0.6 /28. Exit. Do write. Office A is done. Let's move on to Office B, configuring the 10.0.0.16 /28 subnet for management, with .20 for A-switch B1, .21 for B2, and .22 for B3. A-switch B1 first. IP default gateway 10.0.0.17, interface VLAN 99, IP address 10.0.0.20 /28. Exit. Do write. A-switch B2 next. IP default gateway 10.0.0.17, interface VLAN 99, IP address 10.0.0.21 /28. Exit. Do write. And finally, A-switch B3. IP default gateway 10.0.0.17, interface VLAN 99, IP address 10.0.0.22 /28. Exit. Do write. Okay, we've configured a management IP address on each access switch. That's all for step 11. In the remaining steps for this part, steps 12 to 19, we will be configuring HSRP on each office's distribution switches. We need to configure HSRP for 4 subnets in each office. In Office A, we need HSRP for the management subnet, the PC subnet, the phone subnet, and the Wi-Fi subnet. In Office B, we need HSRP for the management subnet, the PC subnet, the phone subnet, and the server subnet. I'll demonstrate the complete configuration for dswitch A1 and A2 in Office A, but for the sake of time, I'll just copy and paste the configurations for Office B. So, steps 12 to 15 focus on Office A. Step 12 says to configure HSRP version 2 group 1 for Office A's management subnet, which is VLAN 99. We should make dswitch A1 the active router by increasing its priority to 5 above the default. The default is 100, so we should make it 105. And then enable preemption on dswitch A1, the active router. The subnet is 10.0.0.0 /28 with .1 as the virtual IP, .2 for dswitch A1, and .3 for A2. So let's configure that on dswitch A1 first. These distribution switches will be the default gateway for hosts in each subnet, and they will use HSRP to provide redundancy. Okay, so on dswitch A1, configure interface VLAN 99. First, I'll configure dswitch A1's own IP address. IP address 10.0.0.2 with a /28 netmask. Then, I'll enable HSRP version 2 with standby version 2. Next, I'll configure the VIP with standby 1 IP 10.0.0.1. Now let's ensure that dswitch A1 becomes the active router by increasing the priority to 105. Standby 1, priority 105. Finally, let's enable preemption, so this switch will always be the active switch as long as it is up and running. Standby 1, preempt. Next, let's configure dswitch A2 side of the management subnet. Interface VLAN 99. dswitch A2's IP is IP address 10.0.0.3 and a /28 netmask. Then enable HSRP v2 with standby version 2. And finally, configure the VIP with standby 1, IP 10.0.0.1. That's all we have to configure on dswitch A2. We can leave it at the default priority since we already raised dswitch A1's priority. And there's no need to configure preemption on the standby router, although you can use the command if you want to. It won't do any harm. So we've configured HSRP for the management subnet. Next, let's move on to step 13, in which we'll configure HSRP v2 for the PC subnet. Once again, dswitch A1 should be the active router. However, notice that it says to configure group 2 instead of group 1. The configurations will be nearly identical, but we will use a different group number and different IP addresses. The subnet is 10.1.0.0/24, with .1 as the VIP, .2 for dswitch A1, and .3 for A2. Let's start with dswitch A1. Interface VLAN 10. First, configure the interface's IP address with IP address 10.1.0.2, 255.255.255.0. Then enable HSRP v2 with standby version 2. Then I'll configure the VIP with standby 2 IP 10.1.0.1. Make sure to use the correct group number here. Then I'll raise the priority with standby 2 priority 105. And finally, standby 2 preempt. Okay, now let's configure dswitch A2 side. Interface VLAN 10, IP address 10.1.0.3/24, standby version 2, standby 2 IP 10.1.0.1. Okay, that's all for A2. Now we have two more HSRP groups to configure for Office A in steps 14 and 15. For these two groups, we will make dswitch A2 the active router instead of A1. Let's start with step 14, configuring HSRP v2 group 3 for the phone subnet. The subnet is 10.2.0.0/24 with .1 as the VIP, .2 for dswitch A1, and .3 for dswitch A2. I'll start with dswitch A2 this time. Interface VLAN 20, IP address 10.2.0.3/24, then enable HSRP v2, standby version 2. Configure the VIP, standby 3 IP 10.2.0.1, and this switch should be the active router, so standby 3 priority 105, standby 3 preempt. And now dswitch A1 side. Interface VLAN 20, IP address 10.2.0.2/24, standby version 2, standby 3 IP 10.2.0.1. Finally, we have one more HSRP group to configure for step 15, the Wi-Fi subnet, VLAN 40. Again, dswitch A2 should be the active router. The subnet is 10.6.0.0/24, with .1 as the VIP, .2 for dswitch A1, and .3 for dswitch A2. And note that the HSRP group is 4. Let's start on dswitch A2. Interface VLAN 40, IP address 10.6.0.3/24, standby version 2, standby 4 IP 10.6.0.1, standby 4 priority 105, standby 4 preempt. And then let's configure dswitch A1 side. Interface VLAN 40, IP address 10.6.0.2/24, standby version 2, standby 4 IP 10.6.0.1. Okay, we finished configuring HSRP in Office A. dswitch A1 is the active router for groups 1 and 2, and dswitch A2 is the active router for groups 3 and 4. Let me save the config with do write and exit to return to global config mode. Then I'll do the same on A2. Do write, exit. Steps 16 to 19 are the same thing, but for Office B. HSRP v2 Group 1 is for the management subnet, VLAN 99. Group 2 is for the PC subnet, VLAN 10. Group 3 is for the phone subnet, VLAN 20. And Group 4 is for the server subnet, VLAN 30. dswitch B1 should be active for groups 1 and 2, and dswitch B2 should be active for groups 3 and 4. Instead of going through the configurations one by one, I'll just copy and paste them from my notepad. So here we are, part 3, steps 16 to 19. dswitch B1 will be primary for HSRP groups 1 and 2, and standby for groups 3 and 4. Let me highlight and copy these configurations. And then go into the CLI of dswitch B1, right-click, paste, exit, do write. And now dswitch B2. Let's look at the commands in the notepad. So this switch will be standby for groups 1 and 2, and active for groups 3 and 4. Let's highlight and copy these commands, go into the CLI of dswitch B2, right-click, paste, exit, do write. Okay, we're finally done with part 3. We configured IP addresses on R1 and all of these switches, configured layer 3 ether channel between C-switch 1 and C-switch 2, and configured various HSRP groups among these distribution switches. Now I'll click Next to move on to part 4. Part 4 is all about Rapid Spanning Tree Protocol. This part shouldn't take so long. In step 1, we'll configure Rapid PVST+ on the access and distribution switches. And then in step 2, we'll enable PortFast and BPDU guard on the appropriate ports. So let's get right into it with step 1. First of all, we should enable Rapid PVST+ on the distribution and access switches. By default, these switches in Packet Tracer run standard PVST+, not the Rapid version. To prove that, I'll go on dswitch A1 and use do show spanning tree. Notice that it says Spanning Tree Enabled Protocol IEEE. Note that this doesn't mean it's running IEEE standard Spanning Tree Protocol. This means it is running Cisco's per VLAN Spanning Tree Plus, PVST Plus. To change it to Rapid PVST Plus, the command is spanning tree mode rapid PVST. And let's double check with do show spanning tree again. Okay, now it says RSTP, meaning Rapid PVST Plus is enabled. Okay, let me highlight the spanning tree mode rapid PVST command and copy it. Now I'll quickly go on to the other switches and paste it in. dswitch A2 first. Right-click, paste. Then dswitch B1. Right-click, paste, and dswitch B2. Right-click, paste, then the access switches. switch A1, right-click, paste, and A2, right-click, paste, and A3. Right-click, paste. Then switch B1. Right-click, paste. Then switch B2. Right-click, paste. And finally, switch B3. Right-click, and paste. Okay, now all of these switches are running Rapid PVST Plus instead of the classic PVST Plus. Now let's look at the sub-steps of step 1. 1A says to ensure that the root bridge for each VLAN aligns with the HSRP active router by configuring the lowest possible SDP priority. So that means a priority of 0. So in Office A, dswitch A1 should be the root for the management VLAN, which is VLAN 99, and the PC's VLAN, which is VLAN 10. And dswitch A2 should be the root for the phone's VLAN, VLAN 20, and the Wi-Fi VLAN, VLAN 40. The same applies for Office B, with the server's VLAN replacing the Wi-Fi VLAN. Okay, and then B says to configure the HSRP standby router for each VLAN with an SDP priority 1 increment above the lowest priority. So the lowest priority is 0. What's 1 increment above that? Well, SDP priority is configured in increments of 4096. So 1 increment above 0 is 4096. Let's configure that on each distribution switch, starting with dswitch A1. So I'll first set its priority to 0 for VLANs 10 and 99, with spanning tree VLAN 1099, priority 0. You can also do it in 2 separate commands, one for VLAN 10 and one for VLAN 99. The effect is the same. Let me double check that it's the root bridge now. VLAN 10 first. Do show spanning tree VLAN 10. Okay, it says this bridge is the root. And then for VLAN 99. Do show spanning tree VLAN 99. Okay, same for this VLAN. Then I'll set its priority to 4096 for VLANs 20 and 40. the phone's VLAN, and the Wi-Fi VLAN. Spanning tree VLAN 20, 40, priority 4096. Okay, that's all for this switch in this part of the lab, so I'll use do write to save the config. Now let's configure dswitch A2. First, I'll set its priority to 0 for VLANs 20 and 40. Spanning tree VLAN 20, 40, priority 0. Next, let's set it to 4096 for VLANs 10 and 99. Spanning tree VLAN 10, 99, priority 4096. And save the config with do write. Now let's do the same thing in Office B. First, I'll set dswitch B1's priority to 0 for the PC's VLAN and the management VLAN, VLANs 10 and 99. Spanning tree VLAN 10, 99, priority 0. And then set it to 4096 for the phone's VLAN and the server's VLAN, VLANs 20 and 30. Spanning tree VLAN 20, 30, priority 4096. And let's save the config with do write. And finally, dswitch B2. First, I'll set the priority to 0 for VLANs 20 and 30. Spanning tree VLAN 20, 30, priority 0. And then to 4096 for VLANs 10 and 99. Spanning tree VLAN 10, 99, priority 4096. And then save the config with do write. Now let's do step 2, which says to enable portfast and BPDU guard on all ports connected to end hosts, including WLC1. Perform the configurations in interface config mode. Okay, so portfast allows ports connected to end hosts to immediately move to the STP forwarding state, without having to wait 30 seconds to transition through listening and learning. You should generally configure it on ports connected to end hosts, so they don't have to wait to access the network after physically connecting to the switch. BPDU guard, on the other hand, is used to disable a port if it receives a spanning tree BPDU. You should configure it on ports connected to end hosts to prevent users from connecting an unauthorized switch to the network. So I'll start on A-switch A1. First, I'll configure portfast and BPDU guard on F01, which is connected to LWAP1. Interface F01, spanning tree portfast, spanning tree BPDU guard enable. And now F02, which is connected to WLC1. Interface F02, spanning tree portfast. Let's pause for a second here. Notice the second warning message. Portfast has been configured on F02, but will only have effect when the interface is in a non-trunking mode. That's a problem. F02 is a trunk port, because it's connected to WLC1 and needs to support the management and Wi-Fi VLANs. Here's the solution. I'll use the up arrow to go back to the command, and then use the question mark. Notice the trunk option. As the description says, this will enable portfast on the interface even in trunk mode. Okay, so spanning tree portfast trunk. There we go. And now I'll enable BPDU guard. Spanning tree BPDU guard enable. Exit. And save the config with do write. Okay, so we're done with A-switch A1. It was a special case because of that trunk port. The other access switches only have one host connected and require the same commands to enable portfast and BPDU guard, so I'll return to my notepad. Here are the commands. Interface F01, spanning tree portfast, spanning tree BPDU guard enable. So I'll copy these commands, and let's paste them into A-switch A2. Right-click, paste, exit, and save with do write. Then A-switch A3. Right-click, paste, exit, do write. And A-switch B1. Right-click, paste, exit, do write. Then B2. Right-click, paste, exit, do write. And finally, A-switch B3. Right-click, paste, exit, do write. Okay, that's all for part 4 of this lab. We enabled Rapid PVST Plus on the distribution and access switches, modified the priority values of the distribution switches for each VLAN to align with the HSRP active and standby routers, and then configured portfast and BPDU guard on the access switches. Now I'll click Next to go to part 5. This part of the lab is all about static and dynamic routing. In step 1, we'll configure OSPF on R1 and the core and distribution switches. Then in step 2, we'll configure default routes on R1 for its internet connections, and then make R1 an ASBR that advertises its default route to other routers in the OSPF domain. So let's get started with step 1. Step 1 says to configure OSPF on R1's LAN-facing interfaces, so these two connected to C-switch 1 and 2, and all core and distribution switches, specifically on all layer 3 interfaces. Now there are a lot of specific instructions below, so before jumping into the configurations, it's important to read all of these. A says to use process ID 1 and area 0. B says to manually configure each device's router ID to match the loopback interface IP. So R1's loopback is 10.0.0.76, C-switch 1's is 77, C-switch 2's is 78, etc. Then C says that, on switches, you should use the network command to match the exact IP address of each interface. In other words, use the network command with a /32 wildcard mask, which is 0.0.0.0, to enable OSPF on each interface. Then D says that you should enable OSPF in interface config mode on R1. You can do that with the IP OSPF1 area 0 command on each interface. Moving on to E, it says to make sure OSPF is enabled on all loopback interfaces too, and they should be passive interfaces. And F says that each distribution switch's SVIs, except the management VLAN SVI, should be passive too. So by default, after enabling OSPF on the distribution switch SVIs, they will send OSPF hello messages out of their SVIs to the LANs, and they will receive each other's hellos and become OSPF neighbors. However, we don't need them to become neighbors 4 times, once for each VLAN. We'll make all SVIs except the management SVI passive, so they will only send hellos out of the management SVI. Finally, G says to configure all physical connections between OSPF neighbors to use a network type that doesn't elect a DR and BDR. In other words, you should configure the point-to-point network type on the interfaces. Note that in Packet Tracer, the necessary command isn't available on the layer 3 port channel interface between C-switch 1 and C-switch 2, so we'll leave this link as the default network type. Okay, so we have a lot of configurations to do. I'll configure the first couple of devices one command at a time in the CLI to walk you through the process, but after that, I'll just copy and paste the commands. So let's open the CLI of R1 and get started. First, I'll create the OSPF process with router OSPF1. Now let's specify R1's router ID. Actually, if I check the current router ID with do show IP OSPF, you can see that the ID is 10.0.0.76, the IP address of its loopback interface. However, step 1b said to manually configure each device's router ID, so I will do that with router ID 10.0.0.76. Okay, there is only one more command to configure in this mode, which is passive interface loopback 0. We haven't enabled OSPF on loopback 0 yet, but let's do that next. The instruction said to activate OSPF in interface config mode on R1, so interface loopback 0. And then activate OSPF with IP OSPF1 area 0. And now we just have to activate OSPF on R1's 2 LAN-facing interfaces, connected to C-switch 1 and C-switch 2. Those are G00 and 01, so interface range G00 to 1. Let's activate OSPF. IP OSPF1 area 0. And then also configure the point-to-point network type. IP OSPF network point-to-point. Okay, that's all for R1. We configured its router ID, made its loopback interface passive, activated OSPF on the appropriate interfaces, and configured the point-to-point network type. Next, I'll go on C-switch 1. First, create the OSPF process with router OSPF1. And like on R1, I'll first configure the router ID with router ID 10.0.0.77, the IP address of its loopback interface. And let's make the loopback interface passive. Passive interface loopback 0. Now for the switches, the instructions say to activate OSPF using the network command with a /32 wildcard mask. So let's see the IP addresses of cswitch1's interfaces. If I use do show IP interface brief like this, the output is full of these interfaces without any IP address. To filter out these interfaces from the output, let me add a pipe to the end of the command, exclude, and then UN to filter any lines that include unassigned. There we go. Now we can only see the interfaces that have an IP address. So let's activate OSPF on these interfaces in order, starting with port channel 1. Network 10.0.0.41, 0.0.0.0, area 0. And now I can simply hit the up arrow to return to that command, and then change the IP address to .34 for the G101 interface. And then, up arrow again, change it to .45 for G111. Up arrow again, .49 for G112, then again for G113, .53. Up arrow again, change it to .57 for G114, and one more time, change it to .77 for loopback 0. Okay, we've activated OSPF on all of cswitch1's interfaces. But there's one more thing to configure on cswitch1. We need to configure the point-to-point network type on its physical ports, G101 and G111, 2, 3, and 4. So, interface range G101, a comma, and then G111 to 4. And configure the network type with IP OSPF network point-to-point. Okay, that's all for cswitch1. Finally, I'll exit and use do write to save the config. The configurations for the rest of the switches are similar, so I'll just copy them from the notepad and then paste them into each device. To repeat what I said before, when you are doing this lab yourself, it's important that you prepare all of these configurations yourself. Otherwise, it's not practice. But for the sake of the video, let's do this to speed things up. The video is long enough as is. So cswitch2's configurations are identical to cswitch1's, just with different IP addresses. So I'll copy them, go into the CLI of cswitch2, and paste them in. Then I'll exit and save the config with do write. Now let's return to the notepad and look at the commands for dswitch-A1. We'll set its router ID, make its loopback interface passive, and also make its SVIs passive for VLANs 10, 20, and 40, but not for the management VLAN, VLAN 99. Then activate OSPF on each interface, and finally configure the point-to-point network type on G111 and 112. Those are the physical links connecting to cswitch1 and 2. So I'll highlight and copy these commands, go to the CLI of dswitch-A1, and paste them. Then exit and do write. Okay, and now let's return to the notepad and look at dswitch-A2's configurations. These are identical to dswitch-A1's, just with different IP addresses. So I'll copy them, go into the CLI of dswitch-A2, and paste them. Then exit and do write. Now before moving on, let's check its OSPF neighbors. Do show IP OSPF neighbor. So it has 3 neighbors. 10.0.0.79 is dswitch-A1. Notice that the interface is VLAN 99. If we didn't make the VLAN 10, 20, and 40 SVIs passive, dswitch-A1 and A2 would become OSPF neighbors with each other 4 times, once for each SVI. That isn't necessary. And notice that because we made G111 and 112 point-to-point, no DR or BDR are elected for the connections with cswitch1 and cswitch2, 10.0.0.77 and 78 here. Okay, now let's do the same for dswitch B1 and B2 in Office B. So I'll return to the notepad. The configurations are basically identical, with different IP addresses of course. And instead of VLAN 40, Office B has VLAN 30, but that's it. So I'll copy these commands for dswitch B1, open its CLI, and paste them. Then I'll exit and do write. And finally, let's return to the notepad and copy the commands for dswitch B2. Once again, these commands are identical, just with different IP addresses. Open the CLI of dswitch B2, paste the commands, and exit, do write. Okay, we're done with step 1, configuring OSPF. Now let's move on to step 2, It says to configure one default route for each of R1's internet connections. They should be recursive routes, meaning they should specify a next hop IP address, but not an exit interface. For review, recursive routes specify only the next hop IP. Directly connected routes specify only the exit interface, and fully specified routes specify both. 2A says to make the route via G010 a floating static route by configuring an AD value 1 greater than the default. And then B says that R1 should function as an ASBR, advertising its default route to other routers in the OSPF domain. Okay, let's go back to the CLI of R1. So R1 has 2 internet connections. Let's see. Do show IP interface brief. There they are, G000 and G010. Both of them have a /30 prefix length. You can confirm that with do show IP interface G000. You can see that here in the second line. Internet address is 203.0.113.2/30. A /30 subnet only has 2 usable addresses, .1 and .2 in this case, so that means the ISP's IP address must be 203.0.113.1. Let's check with do ping 203.0.113.1. Okay, so that should be the next hop IP of one of the routes. And let's verify the other one. Do show IP interface G010. Okay, internet address is 203.0.113.6/30. This is the .4/30 subnet, and the other usable address is .5, which should be the ISP's address. Let's ping it. Do ping 203.0.113.5. Okay, it works. That should be the next hop IP of the other default route. So let's configure those routes. The first one via 203.0.113.1. IP route 0.0.0.0, 0.0.0.0, 203.0.113.1. Okay, that's it. Now let's configure the second one via .5 and make it a floating static route. IP route 0.0.0.0, 0.0.0.0, 203.0.113.5. Now the instructions say to make the AD 1 higher than the default. What's the default administrative distance of a static route in Cisco iOS? It's 1, so let's specify 2 here. So we configured 2 default routes. Let's verify that only one is active in the routing table. Do show IP route. Look down at the bottom, and there it is. 0.0.0.0/0 via 203.0.113.1. Perfect. Finally, let's do step 2B, in which we'll make R1 an OSPF ASBR, so it advertises its default route. To do that, go back to OSPF config mode with router OSPF1, and then use default information originate. And that's it. Finally, I'll use exit and do write. Now, if I go to any of the layer 3 switches, such as dswitch B2, and use do show IP route, I should see the default route. You can see it down at the bottom of the routing table. Notice it has 2 routes installed, one with C-switch 1 as the next hop, and one with C-switch 2 as the next hop. Now if I ping R1's internet IP from this switch, it should work. Do ping 203.0.113.2. Okay, the ping works. Now what about the ISP's IP address? Let's try. Do ping 203.0.113.1. It gets 5 U's in reply, meaning unreachable. The reason for that is dswitch B2 is pinging from a private IP address, which the ISP's router doesn't accept. To solve that, we need to configure NAT, Network Address Translation. So let's click Next in the lab instructions to move on to Part 6. In Part 6 of this lab, we'll configure various network services like DHCP, DNS, NTP, SNMP, syslog, FTP, SSH, and NAT. We've got a lot of configurations to do in this section, so let's get started with Step 1, which says to configure the following DHCP pools on R1 to make it serve as the DHCP server for hosts in Offices A and B. Also, we must exclude the first 10 usable addresses of each pool. So which pools do we need to configure? First, a pool for Office A's management subnet. LWAP1 will lease an IP address from this pool. Then a pool for Office A's PCs. PC1 and PC2 will use this pool. And then a pool for Office A's phones, which Phone 1 and Phone 2 will use. Then we will configure the equivalent management, PC, and phone pools for Office B, and finally a single pool for wireless clients. So all of these pools will use similar commands, just with different IP addresses. I'll configure the first one manually, but then copy and paste the others. But before we configure the pools, let's configure the excluded address ranges, the first 10 addresses of each subnet. To do that, I'll open up my notepad again. So here's Part 6, Step 1. These are the 7 ranges of addresses we'll exclude, in the same order as the instructions. Office A's management, PC, and phone subnets, then Office B's management, PC, and phone subnets, and finally the Wi-Fi subnet. The command is ipdhcp excluded address, followed by the first address in the range, and then the last address in the range. So these commands exclude the first 10 usable host addresses of each subnet, so R1 won't assign them to clients. I'll highlight and copy these commands, and then go into the CLI of R1 and paste them. Now let's configure the DHCP pools. Like I said, I'll do the first one for Office A's management subnet manually. Let's look at the info again. The subnet is 10.0.0.0/28, and the default gateway is 10.0.0.1, which is the HSRP VIP that we configured on dswitch A1 and A2. The domain name is jeremysitlab.com. The DNS server is 10.5.0.4, which is server 1. And then the WLC is 10.0.0.7, WLC1. And note that name, A-management. This has to match, or it won't be marked correctly when you click Check Results. So let's go back to the CLI of R1 and use ipdhcp pool A-management to create the pool. Then use network 10.0.0.0 255.255.255.240 to specify the 10.0.0.0/28 subnet, and default router 10.0.0.1 to specify the default gateway. Next, configure the domain name with domain name jeremysitlab.com. And then I'll specify server 1 as the DNS server with DNS server 10.5.0.4. Finally, we need to specify the WLC address for lightweight access points. Actually, take another look at the network. In Office A, when LWAP1 sends a broadcast message to identify any WLCs in the network, WLC1 will receive that broadcast and respond. So we technically don't need to specify the WLC address in this DHCP pool. However, for Office B's management DHCP pool, it is necessary. When LWAP2 sends a broadcast message, it won't reach WLC1. So we should specify WLC1's IP address in the DHCP pool, so LWAP2 can send a unicast message directly to WLC1 to connect. However, the lab instructions say to configure the WLC address for this pool, so let's go back to the CLI. I'll use the question mark to see the available commands. To specify a WLC address, we have to use the option keyword. After that, specify the option number. The correct number here is option 43, then IP, and then the IP address, 10.0.0.7. So that's the command. Option 43, IP, 10.0.0.7. Okay, so that's the first pool, and the rest will use basically the same commands, so let's go back to the notepad. Here are the commands for the rest of the pools. A PC, A phone, B management, B PC, B phone, and Wi-Fi. I'll highlight and copy these commands, return to the CLI of R1, right-click, and paste, and exit. Okay, so step 1 is done. But if I use do show IP DHCP binding on R1, it won't show any DHCP leases. The reason for that is that clients' broadcast DHCP requests won't reach R1. So in step 2, we'll configure the distribution switches to function as DHCP relay agents, forwarding clients' broadcast messages to R1's loopback 0 IP address, which is 10.0.0.76. To do that, we need the IP helper address command on the interfaces that receive clients' broadcast DHCP messages. In this case, those are the various SVIs on each switch. I'll go back to the notepad to see the commands. On dswitch A1 and A2, we'll use IP helper address 10.0.0.76 on the VLAN 10, 20, 40, and 99 SVIs. And then on B1 and B2, it'll be for VLANs 10, 20, 30, and 99. The thing to note here is that this command must be configured on the correct interface, the interface that receives the broadcast DHCP messages from clients. More specifically, the Layer 3 interface, each SVI in this case, not the physical Layer 2 switch port. Okay, let's copy the commands for Office A, then open the CLI of dswitch A1, and paste the commands in. Exit. Okay, dswitch A2 needs the same commands, so let's open its CLI and paste the commands in. Exit. Then I'll return to the notepad and copy these commands for Office B. The only difference is that it uses VLAN 30 instead of VLAN 40. Now I'll go on to dswitch B1 and paste the commands in. Exit. Finally, dswitch B2. Let's paste the commands in here and exit. Okay, we're done with step 2. Now, hosts should be able to lease IP addresses. To test, I'll go on PC1. From the Desktop tab, click on Command Prompt, and then use ipconfig/renew to send a DHCP discover and lease an IP address. And a few seconds later, it works. Let's try some pings now. How about pinging R1's loopback interface? Ping 10.0.0.76. Okay, the ping works. And how about one of R1's internet interfaces? Ping 203.0.113.2. That ping works as well. However, what if I ping the ISP router at ping 203.0.113.1? As you can see, this ping doesn't work. Once again, this is because we need to configure NAT on R1. That'll be in a later step. But now, let's move on to step 3. In this step, we'll configure some DNS entries on server 1, one for google.com, one for youtube.com, and one for jeremysitlab.com, the 3 most popular sites on the web. And then we'll create another entry mapping www.jeremysitlab.com to jeremysitlab.com. So let's open up server 1 again. And from the Services tab, click on DNS. First, make sure to turn on the DNS service here, or server 1 won't respond to DNS queries. Now let's create those 3 IP address mappings. To map a domain name to an IPv4 address, we need to make an A record, which is the default here. So I'll type google.com for the name, and then let's check that address. 172.253.62.100. Okay, so I'll just highlight the address here, left-click and copy, and then paste it here, and click Add to add the entry. Next, type youtube.com for the name, and let's copy the address here, 152.250.31.93, and paste it in the address box, and add the entry. Finally, type jeremysitlab.com for the domain name, and let's copy the address, 66.235.200.145, and then paste it in the address bar. Okay, so we've created 3 A records mapping names to IP addresses. Now, we have to map a name to another name, and for that we need a CNAME, canonical name record. So in the name box, type www.jeremysitlab.com, and then in the hostname box, type jeremysitlab.com. Okay, we've created the DNS records. Now let's test if DNS works. I'll go back to PC1, and first let's ping server 1 to make sure that PC1 can reach it. Ping 10.5.0.4. Okay, PC1 can reach server 1. Now let's try one of those entries we created. Okay, the ping failed because we still haven't configured NAT, but notice that DNS itself worked. Using DNS, PC1 was able to translate google.com into this IP address. And how about ping jeremysitlab.com? Same thing, the ping doesn't work, but DNS resolution does work. And one more. Ping www.jeremysitlab.com. Same thing. Notice that it was translated to the same IP address as jeremysitlab.com. www.jeremysitlab.com was translated into jeremysitlab.com, which was then translated into this IP address. Next, in step 4, we'll configure all routers and switches to use the domain name jeremysitlab.com and to use server 1 as their DNS server. This requires the same 2 commands on all devices. So once again, I'll just copy and paste the commands from the notepad. Those 2 commands are IP domain name jeremysitlab.com and IP name server 10.5.0.4. I'll copy these commands and then paste them into each device. Feel free to skip ahead in the video. So, R1 first. Right-click, paste, and C-switch 1, right-click, and paste, and then C-switch 2. Moving on to the distribution switches, D-switch A1, D-switch A2, and then D-switch B1, and D-switch B2, and then the access switches, A-switch A1 first, then A-switch A2, and then A3, and then Office B, A-switch B1, A-switch B2, and A-switch B3. And just to test that DNS works on these devices, first let's ping server 1 from here on A-switch B3. Do ping 10.5.0.4. Okay, the ping works, and now let's try do ping google.com. Once again, the ping itself doesn't work, but DNS was able to translate the name into an IP address. Now let's move on to step 5, in which we'll configure NTP. 5a says to make R1 a Stratum 5 NTP server. We can do that with the NTP master command. And then 5b says that R1 should learn the time from NTP server 216.239.35.0. 5c is just a note saying that you don't need to wait for NTP to sync. It can take a very long time, so once you've done the configurations, you can just move on. So let's go on the CLI of R1. To make R1 an NTP server with a specific stratum level, use NTP master followed by the stratum, which should be 5 in this case. So that's the first half. Next, to make R1 sync to an external NTP server, use NTP server followed by the IP address, which is 216.239.35.0. And that's all for step 5. Like I said, NTP takes a very long time to sync, so let's just move on. Step 6 is a continuation of step 5. We'll configure NTP on all core, distribution, and access switches, making them sync to R1. Specifically, they should use the IP address of R1's loopback interface. Additionally, these clients should authenticate R1 using key number 1 and the password CCNA. So first I'll create the authentication key on R1, and then configure the clients. To create the key, the command is NTP authentication key, followed by the key number, which should be 1, MD5, and then the key itself, CCNA. However, that's not enough. We need to specify it as a trusted key with NTP trusted key 1. Okay, that's all for R1. Now let's do the clients, all of the switches. The configurations are identical on all switches, so I'll do one manually and then copy and paste the rest. So let's go on C-switch 1. First, use the same 2 commands we just configured on R1. NTP authentication key 1, MD5, CCNA. And then NTP trusted key 1. So we've created the authentication key and trusted it. Next, let's tell C-switch 1 to sync to R1 while using key number 1 for authentication. The command is NTP server 10.0.0.76 key 1. And that's it. As I said, NTP takes forever to sync, so we won't wait for that. Let's just configure the other switches. So I'll go to the notepad, and here it is. Part 6, Step 6. I'll highlight and copy those 3 commands, and let's go to C-switch 2 next, and paste them in. And now the distribution and access switches. Again, feel free to skip ahead in the video. dswitch A1, dswitch A2, dswitch B1, dswitch B2, and then the access switches, starting with A1, then A switch A2, A switch A3, A switch B1, A switch B2, and A switch B3. Okay, that's all for NTP. Next, in step 7 and 8, we'll configure SNMP and syslog. I'll do these two steps together because all devices need the same commands, so I can just copy and paste them together. Let's see the requirements. Step 7 says to configure the SNMP community string, SNMP string, on all routers and switches. It should allow get messages, but not set messages. So that means it should be a read-only string, rather than a read-write string. Let's configure that on R1 before looking at the syslog requirements. The command to configure an SNMP community string is SNMP server community, followed by the string, SNMP string in this case, and then RO for read-only. That's it. With that configured, an SNMP server should be able to send SNMP get messages to read information from this router. Now let's go back to see the syslog requirements in step 8. It says to send syslog messages to server 1, and messages of all severity levels should be logged. Then, 8b says to enable logging to the buffer and reserve 8,192 bytes of memory for the buffer. So let's go into R1 and configure that. First, we need to send syslog messages to server 1. To enable that, just use logging 10.5.0.4. And we need to ensure that messages of all severity levels are sent. So levels 7, 6, 5, 4, 3, 2, 1, and 0. To configure that, use logging trap debugging. That enables logging at the debugging level, level 7 and below. Finally, we need to enable logging to the buffer, which is stored in local memory on the device. The command to do that is logging buffered, but the instructions also specify that the buffer's size should be 8,192 bytes, so add 8192 to the end of this command. There we go. Let's quickly check that everything is correct with do show logging. So logging to the console, monitor, and buffer are all enabled at level debugging. And if I scroll to the bottom, you can see that the buffer is 8,192 bytes in size. The rest of the devices all need the exact same commands as R1. So let me open up the notepad and copy these commands under Part 6, Step 7 and 8. And now let's paste them into the remaining devices. C-switch 1 first. Then C-switch 2, D-switch A1, D-switch A2, D-switch B1, D-switch B2, and the access switches, starting with A switch A1, A2, A3, A switch B1, A switch B2, and finally, A switch B3. So we've configured SNMP and syslog on all of these devices. Now let's move on to step 9. In step 9, we'll use FTP on R1 to download a new iOS version from server 1. To do so, we'll first configure R1's default FTP credentials in 9A, copy the file from server 1 in 9B, and then reboot R1 using the new iOS version in 9C. So let's do 9A first, which says to configure username and password Cisco on R1. To configure the username, the command is ipftp username, and in this case, the username should be Cisco. And then to configure the password, it's ipftp password Cisco. That's it. Next, let's look closer at step 9b. We should use FTP to copy this file from server 1 to R1's flash drive. So you can copy the file name right here from the instructions, but let's go find it on server 1. From the Services tab on server 1, Click on FTP, and you can see the available files here. Look for C2900 Universal. There it is. So click on the file name, use Ctrl-C to copy, and now let's go back to R1. First, let's verify that R1 can ping server 1. Do ping 10.5.0.4. Okay, connectivity is fine. Now let's copy the file to flash with do copy FTP flash. First, it asks for the address of the remote host. Enter 10.5.0.4 for server 1. Then the source file name, the name of the file on server 1. So I'll paste that file name that I just copied here. And finally, the destination file name. Just hit enter here to accept the default, which is the same as the source file name. Now it'll start copying the file. Just a warning, this is going to take a very long time. It'll take so long that you'll think it's not working, but it is. So if you're doing the lab now, get up, grab a drink, take a break, and come back later. I'll stop the video here and return when the download is complete. Okay, the download is done. I'll use do show flash to view the file. Now let's configure R1 to boot using this new iOS image. First, highlight and copy the file name if you need to. Then, to tell R1 to boot from this file, use boot system flash and then paste the file name. Now, before rebooting the router, it's very important to save the config. Otherwise, the boot system command won't take effect. So use do write. And before rebooting, let's also use do show version and look at the top line of the output, version 15.1. After rebooting, we'll check to make sure that it changes. So I'll use do reload to reboot the router. Now, this can take quite a few minutes on a real device, but fortunately, these routers in Packet Tracer only take about 10 or 15 seconds. Once it has booted up, log in with Cisco and password CCNA. Then enable and password Jeremy's IT Lab. And now let's check the version again with show version. So look at the top line, and there it is. Version 15.5, upgraded from the previous 15.1. Now let's look at the instructions one more time. At the end of step 9C, it says to delete the old iOS file from Flash. So let's view the contents of Flash again with show Flash, and then highlight the file name of the old version, right-click and copy the name, and then delete it with delete Flash with a colon, and then paste the file name here. So delete the file, and let's double check with show Flash once more. Okay, now it's gone, so we're done with step 9. Let's take a look at step 10 next. It says to configure SSH for secure remote access on all routers and switches. Okay, let's read through the requirements. 10A says to use the largest modulus size for the RSA keys. 10B says to allow SSH version 2 connections only. 10C says to create and apply a standard ACL that allows only packets sourced from Office A's PC subnet. So, only PCs in that subnet will be able to use SSH to configure these devices. 10D says we should only allow SSH connections to the VTY lines, no telnet. E says to require users to log in with a local user account when connecting via SSH. And then finally, we must configure synchronous logging on the VTY lines. So this is another step where we have to configure the same thing on all of these devices. First, let's go on R1 and walk through each step. First, I'll return to global config mode with conft. To use SSH, we need to create an RSA key pair. Let's do that with crypto key generate RSA. Now it asks for the key modulus size. This plays a big role in determining the security of the keys. A larger size is more secure. The instruction said to use the largest size available, and as you can see here, that is 4096 bits. So enter 4096 here and press enter. Now I'll use do show IP SSH to check the SSH version. Notice that SSH version 1.99 is enabled. 1.99 isn't actually a version of SSH. It just means that R1 accepts both SSH version 1 and version 2 connections. Let's change that with IP SSH version 2. and confirm with do show IP SSH again. So now R1 will only accept SSH v2 connections. Next, before we configure the VTY lines, let's create that ACL that allows only the Office A PC subnet. The subnet is 10.1.0.0/24, so access list 1 permit 10.1.0.0 0.0.0.255. And that's it. We just need that one entry. The implicit deny will block all other traffic. Now let's configure the VTY lines with line VTY 015. First, I'll apply that ACL. To apply an ACL to an interface, the command is IP access group, but for the VTY lines, it's access class, then the ACL name or number, 1 in this case, and in. Next, I'll allow only SSH connections, no telnet since it isn't secure. Transport input, SSH. And let's require users to log in with a local user account, just like we configured on the console line at the beginning of this lab. Login local. And then enable synchronous logging with logging synchronous. Okay, that's all for R1. I'll exit back to global config mode. The other devices require the same commands, so once again I'll copy and paste them from the notepad. First, generating the keys with cryptokey generate RSA, and then 4096 to specify the modulus size. Enabling SSH version 2, configuring an ACL and applying it to the VTY lines, allowing only SSH, requiring login with a local user account, and enabling synchronous logging. Let's copy these commands, and then paste them into the other devices. C-switch 1 first. Paste in the commands, and exit. Then C-switch 2. Right-click and paste, and then exit. D-switch A1. Right-click, paste, exit. D-switch A2. Right-click, paste, exit. D-switch B1. Right-click, paste, exit. And B2. Right-click, paste, exit. Finally, the access switches, starting with A1. Paste the commands, exit. Then A2. Paste the commands, exit. And A3, right-click, paste, exit. Then A-switch B1, paste the commands, exit. And B2, paste the commands, exit. And finally, A-switch B3, right-click, paste, and exit. Okay, now before moving on, let's test SSH by connecting to one of the devices. I'll go on PC1. From the command prompt, I'll try to ping R1's loopback. Ping 10.0.0.76. Okay, PC1 can reach R1. Now let's SSH. SSH-L Cisco 10.0.0.76. Enter the password CCNA, and we're in. So SSH works from PC1. Now I'll exit out of there. Next, I'll try from PC3. Let's open its command prompt. Because of the ACL we applied, SSH shouldn't work from PC3. It's not in the Office A PC subnet. First, I'll just use ipconfig/renew to make sure that PC3 got an IP address, since we just configured DHCP in this part of the lab. Okay, and next I'll ping R1 with ping 10.0.0.76. Okay, the ping works. Finally, let's try SSH. SSH-L Cisco 10.0.0.76. Connection refused by remote host. So the ACL is working. That's all for step 10. Steps 11 and 12 focus on NAT, Network Address Translation. We'll configure static NAT in step 11, and then pool-based dynamic PAT in step 12. So let's read step 11 first. It says to configure static NAT on R1 to enable hosts on the internet to access server 1 via the IP address 203.0.113.113. So we just need to configure a static NAT statement mapping server 1's inside local address 10.5.0.4 to the inside global address 203.0.113.113. It only takes a single command. Let's open up the CLI of R1 and configure it with IPNAT inside source static, then the inside local address, which is 10.5.0.4, followed by the inside global address, which is 203.0.113.113. Now, we've configured the static NAT statement, but there's still something missing. We need to specify the inside and outside interfaces. R1G000 and G010 are connected to the internet, so I'll make them the outside interfaces. Interface range G000 and G010. IP NAT outside. And then the inside interfaces are G00 and G01, connected to C-switch 1 and C-switch 2. Interface range G00 to 1, IP NAT inside, and exit. Okay, so we've configured static NAT for server 1. That should allow hosts on the internet to communicate with server 1 by sending their packets to 203.0.113.113. It should also allow server 1 to ping hosts on the internet, so let's test that. I'll go back to server 1, and let's open up the command prompt, and then try ping google.com. Okay, the ping doesn't work. Even though server 1 is a DNS server, we have to specify itself as its own DNS server in Packettracer. So go to the config tab and add 10.5.0.4 as the DNS server here. This isn't a part of the lab steps, by the way. I'm just doing it to test. Next, return to the command prompt, and let's try ping google.com again. Okay, now the ping works. So step 11 is done. In step 12, we'll configure dynamic PAT, port address translation, to enable the other hosts in these LANs to communicate over the internet. We will configure pool-based dynamic NAT. So we'll need an ACL to define the appropriate inside local addresses, a NAT pool to define a range of inside global addresses, and then we'll map them to each other with a NAT statement. So let's first create the ACL, looking at step 12a. It says to use standard ACL2 to define the appropriate inside local address ranges in the following order: Office A PCs, Office A phones, Office B PCs, Office B phones, and then Wi-Fi. I'll open the CLI of R1 again, and let's make that ACL. First, I'll permit the Office A PC subnet. Access list 2 permit 10.1.0.0, 0.0.0.255. Then I'll hit the up arrow, and let's change that to 10.2.0.0 for the Office A phone subnet. And then do it again, permitting 10.3.0.0 for the Office B PCs. And then again, configure 10.4.0.0 for the Office B phones. And finally, permit 10.6.0.0/24 for the Wi-Fi subnet. So that ACL defines the range of inside local addresses that will be translated when communicating over the internet. Now let's look at step 12b. We need to define the pool of inside local addresses, the public IP addresses. The pool's name should be pool 1, with a range from 203.0.113.200 to .207, and a /29 net mask. So let's go back onto R1, and create the pool with IPNAT pool, pool 1, and then the starting IP address, 203.0.113.200, and then the ending IP address, 203.0.113.207. Net mask, and then 255.255.255.248 /29. Okay, we've created the ACL and the pool. Now let's do step 12c, which says to map ACL2 to pool 1 and enable PAT, and then confirm that hosts can access the internet. So let's go back to R1 and configure the NAT statement. IPNAT inside, source list 2, pool 1. And then don't forget overload to make it PAT instead of regular dynamic NAT. Okay, the NAT configuration is done. So let's test it out on PC1. From PC1, let's do ping jeremysitlab.com. Okay, the ping works, so our dynamic PAT configuration was correct. Now, step 12d says to verify that internet link failover works by disabling R1G000 and pinging again. However, note the paragraph here. You will need to remove and reconfigure the default information originate command on R1 for this to work. When R1 loses its primary default route and inserts the floating default route into the routing table, it won't automatically advertise the new route into OSPF. As this explanation says, you can use default information originate always to work around this, but it's not available in Packettracer. So let's go on R1 now. I'll disable its G000 interface. Interface G000, shutdown. Now R1 should remove its main default route from the routing table and insert the floating default route instead. Next, let's go into OSPF config mode. Router OSPF1, and then use no default information originate to remove the command, and then reconfigure it again. Default information originate. So R1 should now advertise its new default route to other OSPF routers. Let's just double check that the floating static route actually entered the routing table. Do show IP route. Okay, so down at the bottom of the output, you can see that R1's default route has an AD of 2. This is the floating route we configured earlier in the lab. I'll go on PC1 now and try that ping again. Ping jeremysitlab.com. And it works again. So the failover worked. Now let's go back on R1 and undo that. First, I'll re-enable G000, interface G000, no shutdown, and then configure OSPF. Router OSPF1, no default information originate, default information originate. And now I'll exit. Okay, we have one last step before wrapping up this part of the lab. In step 13, we'll disable CDP on all devices and enable LLDP instead. We also must disable LLDP TX, that's transmission, on each access switch's access port, which is F01. So since this is a fairly simple step, I'll go straight to showing the commands in the notepad. On R1 and the core and distribution switches, we just need to use no CDP run to disable CDP, and then LLDP run to enable LLDP instead. We'll use the same commands on the access switches, but also use no LLDP transmit on each switch's F01 interface. So I'll copy these commands for R1 and the core and distribution switches. And let's go on R1 now. Right-click, paste, and since this is the final step for this part of the lab, I'll use do write to save the config. Then C-switch 1. Right-click, paste, do write. And C-switch 2. Right-click, paste, do write. D-switch A1, right-click, paste, do write. Then A2, right-click, paste, do write. D-switch B1 next. Right-click, paste, do write. And then B2. Right-click, paste, do write. Now let's go back to the notepad and copy the commands for the access switches, disabling LLDP transmission on their F01 interfaces. Let's paste them into A switch A1 first. Right-click, paste, and do write. Then A2, right-click, paste, and do write. And A3, paste the commands and save with do write. Okay, 3 more. On B1, right-click, paste, do write. A switch B2, paste the commands in, do write. And finally, A switch B3. Right-click, paste, and do write. Okay, looking at the completion score, you can see that we're almost done with this lab. There are still 3 sections remaining, but they will be shorter than this one. So let's click on Next to move on to Part 7. In Part 7, our focus is security. We'll configure and apply an extended ACL to limit traffic from Office A's PCs to Office B's PCs in Step 1, and then configure port security, DHCP snooping, and DAI on the access switches. So let's get started with Step 1. It says to configure an extended ACL, Office A to Office B, where appropriate. It should allow ICMP messages from the Office A PCs to the Office B PCs, block all other traffic from the Office A PCs to the Office B PCs, but permit all other traffic. Step 1D says to apply the ACL according to general best practice for extended ACLs. That general best practice is that extended ACLs should be applied as close to the source as possible. Standard ACLs, on the other hand, should generally be applied as close to the destination as possible. In this case, we are filtering traffic from Office A's PCs to Office B's PCs, so the source is Office A. The access switches are layer 2, so we can't apply IP ACLs to their interfaces. So the closest location to the source is the VLAN 10 SVI of dswitch A1 and dswitch A2, the default gateway for the Office A PCs. Currently, dswitch A1 is the HSRP active router, but we should configure and apply the ACL on dswitch A2's VLAN 10 SVI as well, since it must be ready to take over if dswitch A1 fails. So let's configure and apply it on dswitch A1 first, and then we'll do the same on A2. First, let's create the ACL with IP access list extended, Office A to Office B. Now, we need to create 3 entries. One to permit ICMP traffic from the Office A PCs to the Office B PCs, one to deny other traffic from the Office A PCs to the Office B PCs, and then one to permit all other traffic. The Office A PC subnet is 10.1.0.0/24, and the Office B PC subnet is 10.3.0.0/24. So let's configure the first entry. Permit ICMP 10.1.0.0, 0.0.0.255. That's the Office A subnet. 10.3.0.0, 0.0.0.255. That's the Office B subnet. For the second entry, it's deny IP, and then the same subnets. 10.1.0.0, 0.0.0.255, 10.3.0.0, 0.0.0.255. And for the final entry, permit IP any to allow all other traffic. Now let's apply it as close to the source as possible, which is the VLAN 10 SVI, the layer 3 interface that receives packets from hosts in the Office A PC subnet. Interface VLAN 10, IP access group, Office A to Office B, in. Okay, that's all for dswitch A1. I'll use exit and then do write to save the config. Now I'll go on dswitch A2 and configure the same. So first create the ACL. IP access list extended, Office A to Office B. Then the first entry, permitting ICMP. Permit ICMP 10.1.0.0, 0.0.0.255, 10.3.0.0, 0.0.0.255. Then deny other traffic. Deny IP 10.1.0.0, 0.0.0.255, 10.3.0.0, 0.0.0.255. And permit all other traffic. Permit IP any. And then apply it to the VLAN 10 SVI. Interface VLAN 10, IP access group, Office A to Office B, in. Finally, exit and do write. So we're done with step 1. We created and applied an extended ACL as close to the source as possible, filtering traffic from the Office A PC subnet to the Office B PC subnet. Now let's move on to step 2, in which we'll configure port security on the F01 port of each access switch. Let's read the instructions. 2A says to allow the minimum necessary number of MAC addresses on each port. For example, for these ports with a phone and a PC, 2 MAC addresses are needed, one for the phone and one for the PC. The ports connected to LWAPs only need 1 MAC address. The LWAP tunnels all client traffic, so the switch should only see the LWAP's own MAC address. And this note mentions that Server 1 doesn't use virtualization, so it uses only a single MAC address. If it had virtual machines running on it, each VM would have its own MAC address. Okay, then step 2B says to configure a violation mode that blocks invalid traffic without affecting valid traffic. And the switches should send notifications, such as syslog messages or SNMP traps, when invalid traffic is detected. So that's referring to the restrict violation mode. Finally, 2C says that switches should automatically save the secure MAC addresses they learn to the running config. In other words, we must enable sticky MAC address learning. So let's configure a switch A1 manually, and then copy and paste the commands for the others. Port security is configured directly on the interface, so interface F01. First enable it with switch port security, and then enable the restrict violation mode with switch port security violation restrict. And finally, enable sticky MAC address learning with switch port security MAC address sticky. Okay, that's all for a switch A1. I'll exit to return to global config mode. A-switch B1 and B3 also need the same commands, so I'll go to the notepad, and here are the commands. Highlight and copy them, and then I'll open the CLI of A-switch B1 and paste them. And then exit. Then A-switch B3. Paste the commands in, and exit. Now let's configure A-switch A2, A3, and B2. They require an additional command. Let's open up the notepad again. Because these switches connect to a phone and a PC, we need to use the switchport port security maximum 2 command to allow 2 MAC addresses, the PC's MAC address and the phone's MAC address. I didn't configure this command on A-switch A1, B1, or B3 because the default number of allowed addresses is 1, and that's all that's needed on those ports. So I'll highlight and copy these commands, and now go on to A-switch A2 and paste them in. And then exit. Then A-switch A3. Paste the commands, and exit. And A-switch B2. Paste the commands, and exit. Okay, we've enabled port security on the access switches, allowed the minimum necessary number of MAC addresses, and configured the restrict violation mode and sticky learning. Now let's move on to step 3, in which we'll configure DHCP snooping on these switches. There are a few requirements. 3A says to enable DHCP snooping for all active VLANs in each LAN. So VLANs 10, 20, 40, and 99 in Office A, and VLANs 10, 20, 30, and 99 in Office B. Then we must trust the appropriate ports, which are those pointing toward the DHCP server, R1. In other words, we must trust the G01 and G02 uplinks that connect to the distribution layer. Then in 3C, we must disable insertion of option 82, also known as the Relay Agent Information option. Then, we'll set a DHCP rate limit of 15 PPS, packets per second, on untrusted ports. However, A-switch A1's connection to WLC1 should have a 100 PPS limit. Once again, I'll manually configure A-switch A1, and then paste the configurations for the other switches. So, on A-switch A1, I'll first enable DHCP snooping with IP DHCP snooping. However, we also need to enable it on a per VLAN basis, and the command is IP DHCP snooping VLAN 10, 20, 40, 99. Next, I'll disable option 82 insertion with no IP DHCP snooping information option. That's a step that people often forget. It can prevent DHCP from working properly. Okay, next I'll trust the uplinks to the distribution layer. Interface range G01 to 2. IP DHCP snooping trust. Next, let's set rate limits for DHCP messages on untrusted ports. F01 first. Interface F01, IP DHCP snooping, limit rate 15. So if A-switch A1 receives DHCP messages on this interface at a rate greater than 15 packets per second, the interface will be error disabled. And now F02, which is connected to WLC1. Interface F02, IP DHCP snooping, limit rate 100. Okay, that's all. Exit. Now let's open the notepad and see the configurations for the other switches. I'll highlight and copy the commands for A-switch A2 and A3. They're the same as A1, minus the F02 interface, which is disabled on these two switches. Okay, I'll paste these commands into A-switch A2. And then return to global config mode with exit. Next, A-switch A3, right-click, paste, and exit. Okay, let's return to the notepad for the Office B switches. The commands here are almost identical, just replacing VLAN 40 with VLAN 30, the server's VLAN. So after copying these commands, let's paste them into A-switch B1, and then exit, then B2, exit, and finally B3, exit. Okay, step 3 is done. Now let's move on to step 4, in which we'll configure DAI, Dynamic ARP Inspection. We need to enable it for all active VLANs, trust the appropriate ports, and enable all optional validation checks. Once again, let's configure aswitch A1 first. Unlike DHCP snooping, DAI only needs to be enabled per VLAN. You don't need to enable it globally. So first I'll use IP ARP inspection VLAN 10, 20, 40, 99 to enable it. Next, let's enable the optional checks. Usually, DAI checks to make sure a matching entry exists in the DHCP snooping binding table. But you can enable these checks to make it perform a more thorough inspection of ARP messages. The command is IP ARP inspection destination MAC, source MAC, IP. And finally, I'll trust the two uplink ports. Interface range, G01 to 2, IP ARP inspection, trust. Okay, that's all. I'll use exit and then save with do write, since this is the last step for this part. Now I'll open up the notepad and go to part 7, step 4. So here are the commands we just configured on aswitch A1. I'll copy them, and then let's paste them into aswitch A2 and A3. A2 first. Paste the commands, exit, and save with do write. Then A3. Paste the commands, exit, and do write. Now let's go back to the notepad and copy the commands for Office B. The commands are the same, just replacing VLAN 40 with VLAN 30. Enable DAI on each VLAN, enable the optional checks, and then trust G01 and 2. So I'll go on aswitch B1 first, and paste the commands in. And then exit, and save the config with do write. Then B2. Paste the commands, exit, and do write. Finally, B3. Paste the commands, exit, and do write. Okay, we're done with the security section of this lab. We configured and applied an extended ACL, and then configured the Layer 2 security features, port security, DHCP snooping, and dynamic ARP inspection. I'll click Next to move on to Part 8. Part 8 is all about IPv6. However, we're not going to do a full IPv6 configuration, just some IP addresses on R1, C-Switch 1, and C-Switch 2, and a couple of routes on R1. Since this lab is already long enough, let's just test that you know the basic IPv6 configuration commands for the CCNA exam. So in step 1, we'll enable IPv6 routing and configure IPv6 addresses on R1, C-Switch 1, and C-Switch 2. On R1G000, which is connected to the internet, we'll configure 2001 DB8A:2/64, and then B:2/64 on G010, which is also connected to the internet. Then, for the connections between R1 and the core switches, we'll use these specified prefixes, 2001 DB8A1/64 and A2/64, and use EUI64 to automatically generate interface IDs. Finally, for the Ether channel connection between C-Switch 1 and C-Switch 2, we'll enable IPv6 on the interfaces without using the IPv6 address command. In other words, we'll use the IPv6 enable command, which enables IPv6 and generates a link local address. Okay, let's get started by configuring R1. Now, before configuring the interfaces, don't forget to enable IPv6 routing with IPv6 unicast routing. That's a common command to forget. Now I'll configure G000, connected to the internet. Interface G000, IPv6 address 2001 DB8A:2/64. And then G010. Interface G010, IPv6 address 2001 DB8B:2/64. Okay, we've configured R1's internet-connected interfaces. Now let's do the LAN-facing interfaces. Looking back at the instructions again, we need to use this prefix with EUI64 for G00 and this prefix for G01. Let's return to the CLI and do that. Interface G00, IPv6 address 2001 DB8A1:64 EUI64. And then G01. Interface G01, IPv6 address 2001 DB8A2:64 EUI64. Alright, we've configured R1's interfaces. Now let's quickly confirm with do show IPv6 interface brief. Okay, there are the 4 interfaces we just configured, each with a link local address, as well as the global unicast address we configured. Now let's configure C-Switch 1 and C-Switch 2's G101 interfaces. For both of them, we'll use EUI64 just like we did on R1. I'll go on C-Switch 1 first. Before configuring the IP address, let's use IPv6 unicast routing to enable IPv6 routing. You should make a habit of configuring that first so you don't forget. Next, interface G101. IPv6 address 2001 DB8 A1 /64 EUI64. Okay, that's C-Switch 1. Next, I'll go on C-Switch 2. First, enable IPv6 routing, IPv6 unicast routing, and then configure the interface. Interface G101, IPv6 address 2001 DB8 A2 /64 EUI64. Okay, finally, let's do the Ether channel between C-Switch 1 and C-Switch 2. Since I'm already on C-Switch 2, I'll start here. Interface port channel 1. The instructions said to enable IPv6 without using the IPv6 address command, so the command to use here is IPv6 enable. Let's verify the effect of that command. Do show IPv6 interface brief. So look at the port channel 1 interface. Enabling IPv6 with IPv6 enable automatically generates a link local address like this. Okay, now I'll save the config with do write, since this was the last configuration on C-Switch 2. And now I'll go on to C-Switch 1. Interface port channel 1, IPv6 enable, and then save the config, do write. So step 1 is done. We configured IPv6 addresses in 3 different ways. Configuring the exact address, configuring a /64 prefix and using EUI64, and then using IPv6 enable. Now in step 2, we'll configure 2 default static routes on R1, pointing to the internet. We'll configure a recursive static route via nexthop 2001 DB8A :1, the ISP connected to G000, and then a fully specified route via nexthop 2001 DB8B :1, the ISP connected to G010. This second route should be a floating route, with an AD 1 higher than the default. Okay, let's return to R1 to configure those routes. The instructions say the first route should be a recursive route, meaning it should only specify the nexthop IP address. So, IPv6 route :0, that's the equivalent to 0.0.0.0/0 in IPv4, and then the nexthop is 2001 DB8A :1. Now the next route, which must be fully specified, meaning it should specify both the exit interface and the nexthop IP address. It should also be a floating route. So, IPv6 route :0 G010 2001 DB8B :1, and then set the AD to 2 to make it a floating route. Okay, that's it. Let's save with do write. And that's all for part 8. We configured IPv6 addresses on R1, C-Switch 1, and C-Switch 2, and then configured a couple of default routes on R1. I'll click Next to move on to part 9. Finally, we've reached the last part of this lab, in which we'll configure a wireless LAN using the GUI of WLC1. Let's take a look at the steps. First, of course, we have to access the GUI of WLC1, which has the IP address 10.0.0.7. The login is admin with the password adminpw12. In step 2, we'll create a dynamic interface for the Wi-Fi WLAN. Then in step 3, create a wireless LAN. And then finally, we'll verify that both LWAPs have associated with WLC1. There's also a note saying that due to Packet Tracer's limitations, wireless clients won't be able to properly lease an IP address from the Wi-Fi DHCP pool. In my experience, they always lease an IP address from the management DHCP pool in Packet Tracer. Don't worry about it, it's just an issue with Packet Tracer. So let's get started. I'll access WLC1 from PC1. First, I'll open up the command prompt and ping WLC1 just to make sure PC1 can reach it. Ping 10.0.0.7. This should also ensure that all devices have the correct ARP entries. It can be quite slow in Packet Okay, next I'm going to leave the command prompt and open up PC1's web browser. It can take a few seconds. Once the browser opens up, use HTTPS to access WLC1 by typing in the address bar, https://10.0.0.7. Here's the login screen. Click on Login, and then enter the username admin and the password adminpw12. Okay, we're in. Now let's look closer at step 2. We need to configure a dynamic interface for the Wi-Fi WLAN, which is 10.6.0.0/24. The name should simply be Wi-Fi with VLAN number 40. It should use port number 1 on WLC1. Its IP address should be .2 of its subnet, and default gateway .1. Finally, its DHCP server should be 10.0.0.76. Okay, let's configure that on WLC1. To configure the WLC's interfaces, open the Controller tab. Once it loads, click on Interfaces on the left. By default, the WLC has two interfaces, the Management Interface and the Virtual Interface. Let's create a dynamic interface. Scroll to the right of this page and click on New. The first menu has the interface name and VLAN ID. So let's name the interface Wi-Fi and set the VLAN to 40. Then click Apply to move to the next menu. We need to configure a few things here. Scroll down to Physical Information and set the port number to 1. Then under Interface Address, set the IP to 10.6.0.2, the netmask to 255.255.255.0, and the gateway to 10.6.0.1. Finally, set the primary DHCP server to 10.0.0.76, R1's loopback interface. Okay, that's it. Scroll up and click Apply, and then click OK on the pop-up. And we're done. I'll click on Interfaces again to go back to the list of interfaces. And as you can see in the list, the interface has been created. Next, let's look at step 3. We need to create a WLAN with the name and SSID Wi-Fi and ID number of 1. We need to enable it and set WPA2 with AES encryption and a pre-shared key of Cisco 123. Okay, let's go back to WLC1 and configure it. WLANs are created from the WLAN tab, of course. To create a new WLAN, just click on Go here on the right. In the first menu, we can set the profile name, SSID, and ID number. Both of these should simply be Wi-Fi, and the ID should be 1, so we don't have to change that. Okay, click on Apply to move on to the next screen. On this next page, we need to configure a couple of things. First, click the checkbox here to enable the WLAN. Then, we should configure the interface. This WLAN should use the Wi-Fi interface, not the management interface. Okay, after configuring that, click on the Security tab. Let's enable WPA2. From the Layer 2 Security dropdown, select WPA plus WPA2. Then, click on WPA2 Policy. For the encryption, AES is selected by default, so we don't have to change that. Then click on PSK to enable pre-shared key authentication, and configure the PSK as Cisco 123. And that's it. There are additional tabs here, but we don't have to configure them for this lab. Most of the remaining settings don't work in Packet Tracer anyway. So just click on Apply in the top right to apply the settings. All configurations are done. I'll just click on Save Configuration to save them. After saving the configurations, click on Monitor to return to the first screen. If you scroll down, you can see the access points associated with WLC1. There should be 2, LWAP1 and LWAP2. Click here to see a list. And here they are. Okay, I'll do one more thing before finishing up. Let's open up Laptop 1. From the Config tab, click on the Wireless 0 interface. Let's make it associate with LWAP1. So specify the SSID Wi-Fi that we just configured. Under Authentication, click on WPA2 PSK and enter the PSK Cisco123. Finally, select the correct encryption type, AES. After a few seconds, Laptop 1 should associate with LWAP1. However, look back at the note under Step 4 in the instructions once more. Wireless clients won't be able to lease an IP address from the Wi-Fi DHCP pool. The Wi-Fi subnet is 10.6.0.0/24. But look at the IP address Laptop 1 leased. It's in the 10.0.0.0/28 subnet, the Office A management subnet. But as I said, don't worry about it. The configurations we did here are correct. It's just a problem with Packet Tracer. So, we're finally done. As the completion score of 100% here shows, we did all of the steps correctly. To be honest, if you're studying for the CCNA exam, I'd be surprised if you got 100% on the first attempt. This is a huge lab, so you will most likely get a few things wrong. If your score isn't 100%, click on Check Results and then Assessment Items, and then click on Show Incorrect Items. This will show you which commands you got wrong, so you can go back and fix them. Okay, this video has gone on long enough, so let's end it here. This was the Jeremy's IT Lab CCNA Mega Lab. I hope this lab and video were both challenging and helpful. Thanks for watching. Before finishing this video, let me thank my JCNP level channel members who support me through YouTube channel membership. To become a member, please click the Join button under the video. Thanks to Velvet Jacob, George, Nasir Chowdhury, Gustavo Macedo, Marcel Lord, Dragos Hirnea, Zakib Shah, Mayor Salman, Vitalis194, Chance Carter 56, Mark Jackson, Bold 1C1U, Gerald Guillaume, Fristas 1207, Hector Hernandez, Roji Kuriakos, Arpad Konivez, 5 Feet, Owad, Daniel Brown, Jose Alvarez, Hussein Yavuz, Samuel Tavares, Kevin Hayes, Roger Bratseth, Brian Grant, Georgi Gemajev, Cats for Life, Adelson Pereira, Farad69, Joyce Njoroge, Madmark 50484, Alexandru Stratan, Hiago Bicalho, DMJ2, Dear Diso, Kurt Nell, Omid Farakesh, Steve Cox, Jasper Yim, Pedro Hartman, Tricky Mickey 123456, Ivano Capuano, Jefferson Steelflex, Burl Campbell, Abhishek Sahu, Toxic, Wilmer Romero, Sinan Sarisinar, Gio, Daniel Andrade, Mike Crumby, Dragos George, Jairo Francisco, Filip Jovanovic, Random User 7547, Wagner Botelho, Mateusz Wzashinsky, Ruben Hernandez, Electro Jedi, Trevor Goldman, Gavin Paul Tech, Sunny Idigu, Jeffrey C., Chitsinde, Stephen White, Edificare, Dragon J, Fio Fiohain, Dimitrolis, Jean-Marcel Belmont, Mikhail Chapsky, Hemant Jabalpuri, Dariush D., Juan Morales, Jiwoo Cho, Gonzalo Nicolas, Doomed Soul, Christine Schubert, Julio Maya, Ram Shanbag, and Sonu Nayar. Sorry if I pronounced your name incorrectly, but thank you so much for your support. Thanks to you and my other supporters, I am able to make these videos and release them for free on YouTube, so I really appreciate the support. Another great way to support the channel is to like the video, leave a comment, subscribe, and most importantly, share this video with others. So if this video was helpful, I'd appreciate it if you did any of those. Thanks for watching.